Let's talk about warnings about probabilities. Probability, you'll recall, is a number between 0 and 1 that we assign to the likelihood of a particular event. We will use the symbol P of E to represent the probability that event E occurs. Suppose you play the lottery. A certain number has not come up in ages. Should you play this number? After all, it seems that this number is due. No, this fallacy is called the law of averages. If a certain event has not happened as often as it should, then it will happen more often in the future to make up for this? Nah, that's bogus. The law of averages is bogus. It's not like a coin says, man, I've come up heads 10 times in a row. I've got to come up tails next time. Coins don't do that. Lotteries don't do that. Related to this is the law of large numbers, which is valid and is not bogus. If an event A has probability P of A, then as the number of trials gets larger, the actual proportion of times that A occurs approaches P of A. Oh my goodness, that's quite a mouthful. Basically, what we're saying is that if you try an event 10 times, the probability that A occurs is not necessarily going to be P of A. If you try it 100 times, not necessarily going to be P of A. But if you try it 1,000 times, 10,000 times, 1,000,000 times, as you get more and more times, more and more trials, in fact, as the number of trials approaches infinity, the proportion of times that you get A occurring is P of A. Let me show you a real-life example of this. Assuming a coin is fair, the probability that it lands tails is 1/2. I have a Roman coin, and I've flipped it 5,200 times. Here's the sound of me flipping it. Okay, and there's a picture. There's the picture of my actual coin. I flipped it 5,200 times, 50 times a day for 104 days. Here's what happened to the proportion of tails over the course of the 104 days. See, it started off, okay, so you get 27 tails out of 50 that first time. Then it goes down, and then it goes up. And then just after you think, wow, this is not a fair coin because it's somewhere between 52 and 53% tails, now over time it just gradually decreases so that now, after flipping it over 5,000 times, it finally got back under 50% tails. So the coin's a fair coin. And again, if you flip it 5,000 times, 10,000 times, 1,000,000 times, eventually, assuming it's a fair coin, it's going to zero in on 0.5. That's the law of large numbers. Different example. We roll a loaded die. Here are the probabilities of each outcome. Is this possible? What do you think? No, it's not possible. The probabilities don't add up to 1. You've got 3/10, that's 5/10. No, they just add up to 9/10. Probabilities don't add to 1. When you sum up all the probabilities, they have to add to 1. Another example, different probability problem. We randomly pick a card from a deck of 52 cards. Find the probability that we pick a jack or a spade. Now, you might think the probability we pick a jack or a spade is the probability of picking a jack, which is 4 out of 52, plus the probability of picking a spade is 13 out of 52, which would give us 17 out of 52. Is this correct? No, it's not. And here's why. If A and B are two events, then the probability of A or B is the probability of A plus the probability minus the probability of A plus the probability of B minus the probability of the overlap, A and B. So again, probability of A and B are two events, probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Now, the probability of A or B is the probability of A plus the probability of B only when this thing, probability of A and B, is 0. So in other words, the probability of A or B is only going to equal this, probability of A plus the probability of B, when this thing here is 0. In other words, when there's no overlap between A and B. In this case, we say that E and B are disjoint or mutually exclusive. So here's what we mean. This is what the Venn diagram would look like if A and B are disjoint. In other words, if they're mutually exclusive. When that's the case, the probability of A and B, that's 0. So the probability of A or B is indeed just the probability of A plus the probability of B. So again, here's what it looks like when two events are not disjoint, not mutually exclusive. In our case, jack and spade are not disjoint, not mutually exclusive, because you can have a jack of spades. So again, if A and B are two events, we use that probability formula, probability of jack or spade, probability of jack plus probability of spade minus the probability of jack and spade, which is 16 out of 52. That, my friend, is the correct answer. Okay, a different warning about probability. Suppose A and B are disjoint events. Can A and B be independent? No, disjoint events are not independent. They're never independent. And here's why. Two events A and B are independent if the occurrence of A does not affect the probability of B. Okay, but if A and B are disjoint events, then the occurrence of A does affect the probability of B. It makes B impossible, so that the probability of B would then be 0. For example, being a freshman and being a sophomore are disjoint events. You can't be both of them. So they are not independent. Being a sophomore does affect the probability of being a freshman. You know what it does to it? It reduces it down to 0. Because if you're a sophomore, the probability of being a freshman is 0. Okay, so a different warning about probability. We roll a pair of dice. First die comes up 2. That probability is 1/6. Probability that the sum is 9, we've seen that before, it's 4/6. So the probability that the first die comes up 2 and the sum is 9, oh, that's just got to be the product of those two probabilities. 1/6 times 4/6 is 4 out of 36. Is this correct? No, of course not. That's why this section is called Warnings About Probabilities. No, the probability of A and B is the probability of A times the probability of B if A and B are independent. Here, A and B are not independent, so this formula is false. In fact, the probability that the first die is 2 and the sum is 9 is 0, because if the first die is 2, then the maximum possible value of the sum is 8. So this is bogus.